pleasure to introduce Dr. Stephen Bedrick. He's an associate professor in DMICE. His research focuses on biomedical applications for speech and language technologies, with a primary focus on speech and language disorders. His ongoing projects in this area include computational assessment of post-stroke anomia and characterization of language features in autism. The second area of research is machine learning and information retrieval in support of secondary use of electronic medical record data for the purposes of cohort discovery and identification of adverse safety events during pediatric pre-hospital transport. Dr. Bedrick came up through our program, the NLM Fellowship, and then went on to do a postdoc at IC postdoc. Welcome, and thank you for speaking today.
Hey, thanks so much for having me. So nice to get to take my turn contributing to the seminar series. So today I'm going to talk about some very, very, very current work in progress that I have going on. So there'll be some terrifying, sketchy results at the end. But we're going to talk about what I am and what I do, which Karen covered, so I'm actually going to skip that. We're going to talk about aphasia and anomia, because that's the project I'm talking about today, what that is.
Speaker, so you don't have to wait.
Oh, good. That's really good. Then sort of setting the stage for the new stuff I'm going to talk about, we'll talk about some previous work on confrontation naming tests and automating confrontation naming tests. Then, because it's 2024, we'll have to do the, but is it using AI thing? And spoiler, the answer is yes, but kind of. We'll have a potentially long digression about AI and LLMs. And then some terrifying, highly experimental work in progress. So me, what I do, we're going to skip that because Karen covered bases. Okay, aphasia. Aphasia is frequently caused by strokes, can be caused by traumatic brain injuries. It is an acquired neurogenic language disorder, and it affects auditory processing of incoming language and also the ability to produce new language. It's a very common side effect of a stroke, right? So a stroke, you have some kind of interruption to blood flow in the brain, damages parts of the brain. Frequently, parts of the brain that are affected involve motor behavior, but they can also affect speech. Aphasia, at any given time, somewhere between 2.5 and 4 million people. So it's pretty common. That's including strokes, but also other kinds of aphasia. And then a really common deficit in aphasia is what's called anomia. That's difficulty retrieving or producing words. It is a really big deal to have. If anyone's ever met anyone with anomia, it's extremely challenging to get by and communicate with them. And the good news is, because it's such a common consequence of aphasia, and part of aphasia, there's a lot of different ways people assess anomia, and then by using what you learn from assessing it, you can guide therapies and treatments. And there's a lot of improvement can sometimes happen with the right treatment. So it's a pretty big deal to assess anomia. And people in aphasiology have spent a lot of time coming up with really good fine-grained assessment for anomia. Most of them work on top of a psycholinguistic model of word production and retrieval. So we don't obviously know exactly how our brains do word retrieval, but there's a few different psycholinguistic theories. The most common one in aphasiology is called Dell's two-step model of word production. So in Dell's two-step model, step one is in your brain, you have a semantic layer. You think about the thing you want to talk about, say dog. Then there's a lexical layer where you retrieve the word dog. And then there's a phonological layer where you figure out how to go from the word dog to the sounds D-O-G, the whole motor speech apparatus of producing those sounds. It all kind of goes from there. Now, the important thing about Dell's two-step model is each layer can be impacted and the layers interact with each other. And the theory, this is the sort of a theoretical explanation for why some forms of aphasia, you can produce a word that is phonologically related to the word you're trying to say. So you might say mog instead of dog, right? You clearly activated the right word, but the wrong sounds came out. It can go the other way around. You could try to retrieve, have dog be the word, the semantic concept, and the word cat gets activated, right? And then there's also some back and forth stuff. So this was really interesting psycholinguistically as a sidebar. This was also an early example of a connectionist model, which if anyone is old enough to remember the 90s and the 80s in cognitive science and computer science and psychology, That was one of the major branches of AI, symbolic AI and then connectionist AI. And today, the neural models we all use today are descended from these connectionist models, but there's like a weird parallel universe of between machine learning and like cognitive science that thinks about the same things using some of the same ideas, but like in wildly different ways. So Dell's two-step model underlies a lot of common theories of aphasic word production. And so guided from that comes this really standardized assessment instrument, the confrontation naming test. If you're familiar with a neuropsychological assessment from like, say, an ER neurosurgical context, right? You have a naming test like the Boston naming test. Is that?
I know. No, it's probably something.
Oh, okay. Never mind. The tapping is not like my bag hitting a thing. No. Okay. So in a confrontation naming test, the idea is you show someone a picture, and the pictures are usually carefully chosen to have unambiguous names attached to them. And there's a target word for the picture, cat. The person says cat. That's a correct response. That means that all three layers of the word production system are working appropriately. If they say cap, that is a phonological error, right? They said a word that is phonemically related to the target word, but the wrong sounds came out. In this case, that's a lexical phonological error because they produced a thing that is actually a word. If they say dog, that's a semantic error, right? It is semantically related to cat, but the wrong thing came out. And so the key outcomes from a test like this are how many and what type of errors get produced. And that tells you, for example, if someone's deficit is semantic in nature or phonological in nature or both, which of course then guides how you treat. So that's great. The problem is scoring these things is a dang nightmare. The Boston naming test is short. It's like 10 or 15 items or something. It's designed for use in a clinical context, but it's really, really short, so it doesn't give very fine-grained detail. In aphasiological research, the kind of standard test that they like to use is called the Philadelphia naming test, which has 175 items. And you can imagine that takes a long time to both administer and score. And besides the time to administer the scoring, you have to transcribe each production phonemically, a lot of them. You have to determine for each one lexicality, which is sometimes easy, other times isn't. They might say something that sounds like a word like fissile, which is a word, but it's a pretty weird, rare word. And, unless you're administering the test in Los Alamos, New Mexico, the odds that your patient actually said fissile is probably pretty low. But they might have, you don't know. And then determining phonemic similarity, there's a whole very involved process that speech pathologists are trained to do, right? Where you have to align phonemes and know a lot about phonotactics and morphology. And then the one that our group pays a lot of attention to, assessing semantic similarity. Are ambulance and firemen related? Are they? Right? We could have a long argument about whether they are or not, right? Some think cat and dog, yeah, probably. Guitar and cowboy, maybe. Depends where you grew up, depends on how you're asking, right? So the guidebooks for the PNT lay out 6 different categories of relationship with examples of each one to try to constrain that, and it's all been validated and tuned. People get trained to a high degree of standard. Even then, it's a mess. My co-PI at PSU on this project has done a bunch of studies where he gets like 5 SLPs to rate the same things, and we're finding out a lot about lack of agreement. It's also an issue when you have like a cultural or demographic mismatch between the examiner and the patient. It's not always clear. People under 20 or under 30 might not know about Westerns from the 40s, right? That would have a lot of guitars and cowboys together, might not have that association, or they might think that things are related that someone who's 80 years old wouldn't think are related, right? So it's hard. So our group's big goal, and we have an R01 that is just wrapping up, was about to try to automate the scoring of these naming tests and the PNT as a step towards being able to have a more automated administration of them. Also, the grant was to move beyond naming tests into connected speech, which is a whole interesting thing for other reasons. As part of this, we built this tool called Paralg, Paraphasia Algorithms, that does automated PNT scoring. It's great. It takes a target of production, calculates 3 features for each pair, whether they're phonologically related, whether the production was lexical, whether they're semantically related, applies the scoring guidelines, and we basically have like a program that can do this pretty well. We basically have automated the algorithm at this point. It works quite well. For lexicality, we use corpus frequency of a word, and we sort of just decide if something is technically a word because it's in the dictionary, but it's really rare. We're like, okay, it's not a word. We figured out empirically what the right threshold is for that. We implemented computationally the PNT rules for phonology, so we can take the word and find the syllables and the consonant clusters and do the alignment and all of that. The last part was semantic similarity. And when we started the grant in 2015, we used the latest, hottest thing, which were word embedding models, to do that. So word embeddings, people who aren't familiar, are a vector space model of lexical semantics. So each word gets to be a vector in some high dimensional metric space. The space is designed, and this is the machine learning part, is you learn a space where words that are similar are close together in that space. Now, similar can mean a lot of different things, right? What makes two words similar is not always easy or straightforward. The way that, I even have a little example, right? So in the space, dog is close to cat and horse and far away from words like person, right? This is projected down to 2 dimensions, obviously. There's a lot of different ways to do these, and the way that you build them depends on what you care about in terms of similarity. Word2Vec was one of the first of the current generation of these. It was actually, going back to my theme of connectionist stuff from the 80s, some of the earliest uses of connectionist models of language were for this kind of purpose, but everyone kind of forgot about them for 20 years. But when they rediscovered them in the 2010s, Word2Vec was the first one that came out, and they kind of punted on the question of similarity, and they went back to the Firthian distributional semantics hypothesis of words that occur together in similar contexts must mean similar things. So words like dog and cat occur in a lot of very similar contexts in language, whereas words like computer occur in different contexts. And so it was able to infer from that. And it turns out to work surprisingly, but way better than it has any reason to, and became useful for a lot of things. So for our purposes, we said, okay, the target is cat, the person said queen, we take the similarity between those two words, and then we just, over some data set of examples, we found what the right threshold was. And we found that most of the time, if Word2Vec said the words were so-and-so close together, it turned out that they were related according to the PNT rules. So we sort of just had a threshold classifier that actually worked pretty well. So that was the missing piece to our puzzle. We had a semantic similarity classifier, and our system was able to get about sensitivity specificity of 0.75, 0.95, macro averaged across all of the different PNT error categories. So that's phonological, semantic, a few different other variations. And in one sense, that's not great. In another sense, it's actually really good. The cases where it was wrong were ones that, by and large, the humans were okay with a few exceptions that I'll talk about in a minute. And it was certainly like a good first start. So we published that and then started working on how we could fix it, improve it. When we did an error analysis, we started looking at what worked and what didn't work. Things like van, Word2Vec did a pretty good job getting things like bus, truck, car were close together with van, close enough that our classifier said they were related. That's the good news. Bad news is some other words it really struggled with. And this was one that drove us nuts because the target word is glass. For some reason, we kept consistently missing cup. Cup wasn't showing up as being related. We could not figure out why. Similarly, hat and head kept not being related. Our classifier insisted that they weren't related. We could not figure out why. And it turns out when we looked at the nearest neighbors of cup in Word2Vec, we saw that the closest things were championships, super cup, tournament, IROC, which is a racing thing. Because it was trained on newspapers, it thought that cup was like a trophy. And the nearest neighbors of head were things like chairman, director, chief secretary. The head of the IMF today announced blah, 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 blah. So the problem that we ran up against was that Word2Vec didn't know about polysemy, didn't know about synonyms, and our model only knew about the New York Times. Okay, so we fixed that. By the time we got to this point in the project, there were new kinds of word embeddings that knew about context. The one that everyone found a lot that became the standard for several years was called BERT. And BERT and its family of word embeddings make contextual word embeddings, right? So these mean that the actual vector you get out is dependent on the context where the word occurs. So in this case, even though head is the same word, it would get a different vector in both of these two situations. So that's one of the reasons why BERT did a lot better than Word2Vec at many NLP tasks. And then, so we used that, we embedded stuff in there. We actually got, the citation's really small. This is from our JSL HR paper last year. We got a 6% bump, but it was like the 6% that our mycopia at PSU kept saying, like, guys, this thing, I can't use it. It thinks that hat and head aren't related. No one's going to use this, go back to the drawing board. So it was an important 6%. And as another example, seal was another polysemous one that gave us a lot of trouble. And in our Word2Vec model, the colors are a little hard to see on the screen here, unfortunately, but the red ones are words that were not related. The green ones are the words that should have been related. And we can see there's not a lot of space, not a lot of separation in this projection of the space. Like, there's a bunch of words that are close together, seal, that still, there are some words that are far away from seal that should be closer, and there's words that are close together with seal that maybe shouldn't be. Although I would argue that eel and seal should be related, but that's a different matter. Our BERT model, because we did a bunch of fine tuning and we actually taught it learned a lot about the task, we got much better separation, and that's why we got the better performance. So from there, we're like, okay, we're done with the PNP. We're going to move on to connected speech. Let's get on to aims 2 and 3 of the grant. We're like 4 years in. We should probably do the other aims, at some point. We went on a whole side quest about speech recognition to automate and other aspects of this test. It was great. Everything was going fine. But in the last couple of weeks, for totally valid and scientific reasons that have nothing to do with hype or fear of missing out or anything, we decided to see if we could get an LLM to do this. The actual conversation went more like this. My co-PI called me up and said, hey, Steve, I just tried ChatGPT on a few of our PNT items, and it actually did really, really well. And I was like, okay. And he's like, what should we tell the NIH when the reviewers say, why should we fund this? ChatGPT can do it. What should we tell them? And, at that point, I had this is the bad place, realization, and this is the same thing that every one of my NLP colleagues has been having on repeat over the last 2 years. A collaborator calls you up and says, so ChatGPT can do aims 1 and 2 of our grant. Why do we need you anymore? And so we decided, okay, we'll give it a try. If for no other reason than that way we can say we tried it and it didn't work, or we tried it and it was amazing, we should just be using it for everything now. But here, let's do a little record scratch pause. Let's talk about LLMs, because we've had a few seminars about them at kind of a higher level, but I think it's a good point to zoom in a little bit. So that was the yes, but is it using AI? We weren't using generative AI, but we were using AI, but okay, now we're going to really use AI. So now it's time for a little bit of a digression about AI. I promise it won't be a Grandpa Simpson long rambling story. Okay, so language models. We've heard a lot about LLMs, but I have not seen a DMICE seminar where we actually explain what the heck a language model even is. So we're going to do that today a little bit before I get back to naming tests. Here's a sentence. I was late assigning the... What word would come next? Anybody?
Homework.
Homework, yes. If I had instead said I was late assigning the purple, that would be weird, right? Like that would be nonsensical. If I'd asked you to pick the 10 words that could have come after assigning the, nobody would have picked purple. So if we have sentences A and B, another way to think about this is the probability of sentence B is lower than the probability of sentence A. We haven't really talked about like what it means for a sentence to be high or low probability, but just intuitively we can imagine in the universe of sentences that could be said, A is way more likely than B. If we reached into the bucket of sentences and pulled out a sentence, we'd draw the first one way more times than the second one. The observation here is that language is not random. This is an observation that actually goes back quite a ways. So Chomsky did a lot of work in the 50s on, formal grammars and generative grammars and things like that, all based around this idea. So when we talk about a language model then, a language model is just any kind of statistical model of the probability of a sequence of words, the probability of a sentence. We can express it in terms of the joint probability of a specific sequence of words, right? That's one thing we can do with a language model. As you remember your probability, we can also frame a joint probability conditionally, right? We can do a conditional probability of a word given its preceding history. Because that can get really long, we'll see P of W given H a lot. That's word given some history. As a sidebar, it's worth just reiterating what we even mean by the word model here, because model is on one of my list of danger words that means like 10 things in different contexts. So when I say model, I mean it in the sense of a simplified abstracted representation of a thing, right? Where some aspects of the thing are preserved and others are removed. This is true for any, this is basically, when we talk about a statistical model of something, right? That's really what we're talking about. When we do a linear regression model of a disease with predictors, we know there's a lot of stuff that isn't going, there's other things that affect it, right? We're just choosing these 4 predictors that tell us about the risk of this disease, right? So we're making choices about how to build a model. Models always have a particular purpose, and that informs what we decide to abstract. So here's a model of an airplane. This is not an airplane. This is a model of an airplane that is very, very accurate in some dimensions and not others, right? There's no doors, there's no landing gear, but the shape of the wings is very, very accurate and precise, right? But there's no painting on it. Who cares what the livery of the airplane is, right? This is for wind tunnel testing. Here's a model of an airplane that is not aerodynamically accurate, but is very accurate with the painting and where the doors are and where the windows are, because it's for a different purpose. It's for having people argue about what color the logo should be and where it should go on the airplane. The first one's for, where do we put the wings so the plane flies? Neither one is a better model of the airplane. That's a nonsensical way to think about it. They're designed for a particular purpose, and you made different choices going into it and out of it. So a language model is that, right? We've decided that some aspects of language are important, other ones aren't. We're going to basically find some way to fit all of language into a computer, and we're going to leave a lot of stuff on the table while we do it. So assuming we have a language model, like forget how to make one for a second. If we have one, a statistical model of P of X, where X is a sequence of letters, what can we do with it? We can compare the probability of different strings, right? And that might be useful for, say, a speech recognition system where you heard maybe 4 different possible things you might have heard if it's a noisy room, and you have to decide which one's more likely, right? The classic is how to recognize speech and how to wreck a nice beach. Right? If you say them quickly together, they sound very similar, but one is a much more likely sentence, right? We can also sample new strings from that distribution, which of course is very important for what we like to do now with large language models and ChatGPT and all of that other stuff, where we're generating new language. How do we make one of these? The easiest way is to count. We get a bunch of text and we start counting. So if we have a sequence, its water is so transparent that we want to know how likely the is to be the next word out of all the words that could come next, right? That's the conditional probability formulation. We can estimate that by counting. If we have a bunch of text, we can count how many times the comes after its water is so transparent that, divided by how many times do we see any sentence, any sequence of its water is so transparent that a, the, it, when, blah, 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 right? That's a maximum likelihood estimate of that conditional probability. Obviously, there's some limitations there, right? If you have a long sequence, that might not, that denominator might not be very large, so you might get a really unstable estimate, but this will work. If you have infinite data, this will totally work. And we just count it up like so. We can cheat. It turns out in English, we don't need the entire sentence. English does a lot of work with word order. And so if we have the most recent history, we can actually get a lot of the information we need to predict the next word. And so we can use the chain rule and decompose, a word given all of its history into a word given, the previous history times previous history minus one, all the way back to the beginning. And that's another way to get around not having infinite data. We can cheat even further and ignore everything other than the word that came before our history words. So now we throw away most of our history and just have one word back. That's a order 2 Markov assumption, if anyone is interested. And when we do that, we can really easily compute estimates, right? So here, if we want to know the likelihood of a sentence starting with I, right, in this tiny little toy corpus of green eggs and ham, we just count up how many times do we see, a sentence starting with I divided by all the sentences, we get a 2/3 probability. Okay. Now, you might imagine that throwing away all that history, we do lose a lot of important information. How much are we actually losing? How much history do we really need? Well, if we take a unigram model that has history of 0, right, only knows how many times did this word occur in the corpus at all. This is from Pride and Prejudice is what I trained this one on, and start drawing words out of the bucket. We see gobbledygook. We don't see total mess, right? The word the is still more common in here, right? We see infrequent words infrequently. We see frequent words frequently, but there's no syntax. There's no semantics. It makes no sense. If we allow bigrams, one word back, right? If each word is based on the preceding word, as you can see, pairs of words are sensical. Once we get to 3 words, it starts to break down and overall makes no sense. Trigrams, this is actually starting to make a little bit more sense, at least syntactically, right? These are kind of syntactically valid sentences for the most part. They still make no sense, but in English, a lot of phrases are 3 words long, right? And a lot of our rules for grammar, for simple sentences, 3 words are enough. If we go to 4 words, now we're getting something that actually scans. You have to read that whole sentence to realize it doesn't make any sense, right? Different languages, this would work differently. Like Latin has free word order, and so this would not work in Latin. But in English or French or something like that, we're pretty good. So 4grams can get pretty good. And so that means then, if I have a 4-gram model and I want to know, is this possible transcription more likely than not possible transcription, 4grams might be enough, right? And that's good because 4grams over a big corpus is a large amount of data, but not as much as 10 grams or something, right? And 4grams is enough that it'll be pretty stable. So for a long time, that's how language modeling worked, is you counted stuff and then you did various tricks to deal with missing counts or sequences that you've never seen before to get better and more stable estimates. Can we do better than counting? Yes. Another way to do this is with a machine learning model. You can take an SVM and you can train an SVM to say, okay, here's the preceding 4 words, predict the next word in a multi-way classification out of all the possible words. And you can do that with a Maxent model. You can do it with an SVM. And those are called discriminative language models, as opposed to what we were talking about before, generative language models, not in the generative AI sense, but in the generative statistical modeling sense. Of course, you can also use neural networks to do this. That was actually one of the first applications. If you go back to the original paper for recurrent neural networks, this was a thing that they did with it, was see, hey, look, we can use it to predict words in a language model. And you can do it with a simple feed-forward network, where you give it, the preceding 4 words of context and it does a multi-way prediction. That's just a fancier version of what I described with an SVM. You can use a recurrent neural network where you have a hidden state, and as you work your way through a sequence of words, it has access to the preceding words and predicts the next word in an RNN or LSTM fashion. And then, of course, you can use the transformer architecture to do it as well. And that is basically it's an extension of the RNN architecture. And the important thing to know is basically all of the LLMs that we know and love, ChatGPT, et cetera, those are all using the transformer architecture for a variety of reasons that turn out to be a really, really good architecture for this kind of thing, for certain categories of use cases. So that's a language model for like PFX. How about generating new text? What do we do? So the example that I showed of the Pride and Prejudice text was what's called a Markov chain decoding, right? At each step, you've got some distribution of words, maybe based on the past 4 examples or based on unigrams, and you just sample, you draw from the hat what the next word is. That is an example of a greedy decoder, we would call it. And this is how one of the ways to decode from a large language model. You just, at each point through your history, you just pick the single most likely word that comes next, 1 word at a time. And then you add that to your history, recompute your new history, draw your next word, add it to the history, do your next word, 1 thing at a time. Another way is sampling. I guess what I said a minute ago about Markov chains is actually the sampling example. The sampling is instead of picking the most likely, you sample according to some scheme. You roll dice, you draw from a hat. There's a bunch of different ways to do the sampling, but it's with some random piece to it. One of the reasons why we get inconsistent output from ChatGPT whenever we ask it a different question is because of the sampling effect, right? It's because as it produces the text, it's, imagine like a choose your own adventure book. It's going down a different branch of the choose your own adventure each time. And then the third common way is some variation on what's called beam search, which is an old technique from speech recognition and sort of classical AI, where you sort of explore, somewhere kind of between gradient and sampling, but you maybe draw the top 3 most likely, and now you have 3 branches, 3 histories, and then across those you draw the for each history. Now you have 3 next most likely tokens to draw, and then you say, okay, of all my possible paths, pick the 3 best and repeat. You sort of have like a branching, dropping the worst branches, keeping the best ones, branching again, dropping the worst branches, keeping the best ones, going and going and going. And that's called beam search. There's not necessarily a right or wrong way to do it. They all have different trade-offs. Greedy decoding tends to give kind of boring, repetitive text. Sampling gives you unreliable text. So it's kind of a, you get to pick. Okay, So that is what's going on in any language model, no matter how big or complicated. It doesn't matter whether it's the fancy ones from Google we heard about the other week, or the tiny one running on my laptop, or the one that you build in my class. You're just doing conditional probability of a word given a history and moving on. Count-based RNNs, transformers, all they're trying to do is model the distributions of their training data, right? And all they're doing when they generate text is just one token at a time. That's all, nothing fancy happening. It is not magic. Like, that's the main thing I want everyone to take away from thinking about this, that any like fancy AI sitting on top of a language model, I call it the 3 raccoons in a trench coat model of AI, because like, it's not AI in the way that if you like went back in time to 1992 and asked anyone who does AI, hey, what's AI? Like, they wouldn't, like, that's not AI, right? It's not reasoning, it's not thinking, it's raccoons in a trench coat. It does, however, it does kind of, work for a lot of things. So we have to ask, what are some differences between LLMs and count-based LLMs? So one is number of parameters. Your account-based LM, your vocabulary is going to be in the hundreds of thousands of words. Parameter counts might be in the single-digit millions, right? Think about how many words there are. You have to have a probability for each word, plus a little bit of times you've seen that word in some kind of historical context. You might have, millions to tens of millions of probabilities to keep track of. Pre-trained language models like BERT are in the hundreds of millions of parameters. A small large language model would be, say, 2 to 7 billion parameters. So that's a few orders of magnitude more. A big model like GPT-4 is nobody really knows, but it's definitely in the hundreds of billions of parameters, probably hundreds of billions with a B, possibly more. So, quantity has a quality all its own, I believe is how the saying goes, right? To the extent that there is a theory of LLMs, the theory is you get like a really large number of parameters and magic happens. Personally, I am uncomfortable with that, but it is also hard to argue with the fact that more parameters does seem to make things go. The other big difference is representation of history. So an account-based LM, all it knows about history is that these 5 words happened, and it knows the probabilities of those 5 words happening in that sequence. And LLM has a much richer representation of history. A lot of the parameters that it's learning, it's not just learning count, it's learning about relationships between things that it's seen. So to the extent that we can understand what its representation of the history looks like, it's definitely a lot more sophisticated. It has things about syntax that it's learned. It has things about relationships between words. So there's a lot more stuff going on there. The way the decision rule is computed is also a lot more involved. So with account-based LM, we're just computing that conditional probability the normal way. A large language model has like a big nonlinear function happening to decide what the best next word is. So again, we don't know exactly what that means or is doing, but we know it's a lot more involved. And so that's probably good. But the what that's being computed is very, very, very similar, right? At the end of the day, all it's predicting is probabilities. And so that's a really important thing to keep in mind, because now that we've looked under that hood, what don't we see? Not a database, not an information retrieval system, right? What I mean by that is there's no explicit representation of that data. So if you look inside a relational database or inside a count-based LM, what we see is it has an explicit representation of what it knows, right? A relational database has tables of facts in it. An IR system has an index of words that occur in documents together, right? Explicitly and formally. LLMs don't have that. They have a bunch of continuous points in some space that who knows what it means. So that means that it's really hard to know what might or might not be present. And that's one of the reasons why citations are such a struggle for large language models, because fundamentally they don't have citations in them, right? They have things that if you squint at them, it might decide to interpret as a citation, or it might not, who knows, right? It's just qualitatively different. LLMs, because of this also, because they don't have this explicit representation, they're very susceptible to recall and frequency bias, because so much of what they know about their input is encoded in that representation of the history. Stuff that's close to the end of the history gets a lot more weight. The other difference is that LLMs aren't doing reasoning or inference in the traditional sense of the word, right? When we think traditionally about computers and reasoning, we think about like propositional logic, right? And decision trees and reasoning algorithms with rules and inference and like all these things that we would have learned in like a classical symbolic AI class, or that you would learn in a philosophy class about reasoning. And that's not, an LLM obviously is doing some things that turn out to have a similar end effect, but it's definitely not doing those things in the same way under the hood. It's just a sequence of tokens on context. We also, and this is where it gets important for using these things for useful things, there's no explicit query output syntax, right? An SQL database has an explicit input and output syntax. LLMs don't. You can train an LLM to expect input to come in a certain way and train it to generate certain kinds of output in a more, you can train it that certain kinds of output are more probable, right? But that's very, very different from like literally building a SQL database from the ground up where all it ever knows about is SQL as the input, right? These are different. And then the one that really drives me nuts from a practical standpoint is that there's no delineation between what I call the structural form and the semantic content, right? Like it's, both are just aspects of the data. If we train out a bunch of JSON data or if we train out a bunch of XML documents, it doesn't know what those things mean. It doesn't know that the structure is important. It will hopefully figure out that the structure is important as a side effect of its training, but it doesn't know that there's a difference between the open and closed tags and what's inside the tag, except insofar as it figures it out from training, right? And again, that's a big difference from a traditional computer program and a big difference of how we're used to thinking about programs and programming, right? Likewise, when we ask it for output in XML or in JSON, you know, yeah, it might actually make it. In fact, nowadays, because it's a common thing, it often does make valid JSON or XML output, but it doesn't know that it's doing that. It doesn't know why it needs to do that, and we can't rely on it doing that if those distinctions make sense. I realize that's a little fuzzy, but we'll see about that. So I posit that our mental model, or the model, if you read like popular press articles about AI, that the model that it puts in your head of how these things work is just wrong. They don't know things, they don't think things, they don't answer questions. They do produce semantically meaningful output, right? But to the extent that they do, that's just an artifact of their training data and the generation context. And we can see that if you ask to get the output in a different form, it'll give you the output in a different form, right? It's not a property of what the model actually understands. It's a property of what we ask it to do. Just a suffix given a prefix. So that means the name of the game to getting useful work out of them is how do we get our suffix or prefix set up so that the suffix that we want is the most likely one that comes, right? A trivial example is specifying in the prefix, by the way, the output has to be in JSON format, right? What we're doing there is we're basically adding to the context for generation extra things that make it think that JSON is what we want, right? We're tweaking on that. So I'll say that at this point, everybody, and I'm including like everybody in this, we're all doing alchemy with LLMs, not science, right? So, you know, we're all at the like, oh my God, this is shiny. Well, how does it work? Who even knows? Let's try throwing things in to see what happens, you know, stage. No reproducibility, lots of trial and error. The ground under our feet is always changing, right? There's a new model every week that has wildly different performance characteristics and capabilities. Very little transparency, lack of validated theories to apply, right? We're very much at a like, you know, in 2001, you know, with the monkeys who are like hitting the monolith. Did you have a question? Yeah.
I have a quick question. Based on what you explained so far, even if you give constraints in the prompt, there's no way to guarantee that by 100% by
right.
logic the LLM gives you or adheres to your prompt. Is that what you're saying?
Yes and no. So no, in terms of the structure of the LLM itself, there's no way to guarantee it. To work around that problem, and I'll have an example of this in a little bit, people have built software tools that help. So the one way to do it is by putting hard constraints on the decoding. So for example, there's software tools that we'll talk about in a little bit that let you basically say, you know, for sure the answer needs to be either yes or no. Now the way those are implemented is if you think about the decoding, right, picking what's the most likely thing that comes next. Well, the way to cheat is just zero out the probabilities of everything other than yes and no, and renormalize your probabilities and sample from there. And you'll only get yes or no out. Will it be the right answer? Who knows, right? But a lot of the stuff about imposing more structure on the output of LLMs, that's sort of the trick they use. And it can get a lot more sophisticated. People have done things where you can basically write a context-free grammar and the decoding knows about your CFG and then will impose it'll do that same trick of like zeroing out probabilities of things that aren't valid according to your grammar. And I love those tools and I use them, but that is a complete and total hack. And that is not the same thing as the model actually knowing that I want output according to this grammar, right? It's a hack that gets useful output and is super valuable and important, but it is very, very different from going around saying my model can produce XML and look, it knows what XML means in the same way that if I have a programmer working for me and I say, hey, write a program to make me XML, they'll actually make it write XML, right? So at a practical level, those kinds of hacks, what do you have to do? Or you can spend a lot of time crafting your prompts to be very, very specific. People have found that putting your prompt in all caps on ChatGPT is helpful. Yelling at the LLM, yeah, that to me, like that is what I'm talking about when I say alchemy. Like that is nonsense. I also love this Bruegel painting, by the way, of Alchemist, just because it's like, this is even more, like it's less reverent and it's like there's chaos happening and their kids are climbing into the closet doing God only knows what while the adults are playing with LLMs, and there's like people's shirts falling apart because they've got, you know, chemicals on them and there's like stuff happening in chaos. That's what I feel like the LLM landscape is. Okay, so that's my digression. Back to science. When we left off, I was in the bad place, or I'd realized that I was in the bad place because now I was going to have to deal with all of that alchemy stuff to basically revisit aim one of my grant when we'd already solved it using tools that we understood. But we thought about it a little bit more, and we actually realized there were some good reasons to try an LLM for this, for our naming test, right? One, item-specific context. Some of the items on the PNT that are really problematic, right? Like people, like the ones where there's a lot of disagreement about, you know, how to interpret the image, or ones where the where there's like strong polysemy, or for example, if we want to say, hey, yeah, if they say the item is guitar, and you know, yeah, okay, if they say something cowboy related, that's also fine, right? The kinds of things that if you're a lab doing physiology, you will have built up your own internal annotation guidelines for how to score this. You know, your house rules, for example, of we allow cowboy and guitar in this lab. Well, under our BERT and word defect framings, there's no way to get that information into BERT. Like that just isn't a thing. With an LLM, we could just tell them. I mean, that's kind of cool, right? Like that, you know, back to like weird science and alchemy, but it is kind of a compelling idea. Patient-specific context. If we can tell it, hey, by the way, this patient is, you know, young, so they're not going to know about this old-timey thing. Or, hey, this patient isn't from the US, they're from England. And in England, they call it or whatever over there, right? We could tell the LLM that, and maybe it would be able to figure something useful out from that. Whereas BERT, no chance. Fine-grained output. We set up BERT like just like a four-way classifier, right? Is it this, or this? With the LLM, we can do it that way. We can also ask it, you know, for more fine-grained, detailed things that'd be a huge pain in the neck for a human to do. Like, hey, is this a synonym, or is it a category coordinate relationship, or is it a subordinate relationship? You know, we could go down the list of the rules in the PNT and ask the LLM for that information, which would be really, really valuable. So we thought there's that. And also, we'd had some recent luck with LLMs for other things on aims 2 and 3 of our grant, using it for connected speech. So we thought, all right, let's give it a try. So how do we get an LLM to score a naming test? The same way we get it to do anything, we prompt it, right? Prompt engineering, right? That's the hot buzzword. That is just a fancy way of saying, how do I get my input text to ensure that the output text is close as possible to what I want, right? In terms of semantic content and structural form. There's a lot of different kind of ways people have tried to organize and typologize prompts, but I kind of like this table just because it shows a bunch of different kind of general patterns and examples of prompts. So an example of how to get, for example, okay, I don't have a pointer, but you know, that first one there for sentiment classification, if you know that it's about movies, you could set up a prompt that looks like, you know, you take the movie review and then you could have a summative sentence, the movie is blank, and ask the system to generate what blank should be. And if you really want to constrain it to, you know, 1 star through 0 stars, you could have the output space be constrained as well in some way. And you can see a number of ways to set up different kinds of classification problems as prompts. Obviously, any one of these we could do a different way. And that's part of the ridiculous thing about prompting is there's like no single right way to do it. You essentially have an infinite number of possibilities, which is kind of maddening. And so less formally, we can think of the prompt. It's just the context. It's the representation of the context that we think the model is going to need to answer the thing. Importantly, because the model doesn't have anything other than the context, right? It doesn't have anything other than that prompt to go on about what we want it to do. Anything that we want the model to do has to go in that prompt, right? We're trying to craft this historical context to make it look, like the natural continuation in text is our answer, which is a little weird. It matters a lot how you do it. This from a paper that looked at prompt stability, and they tried on the right, we see 10 different ways of formatting the same prompt, and the wildly varying performance that we got, or that the authors got, based on the different, for the same inputs, depending on the prompt format. So, to me, that makes the hair on the back of my neck stand up. And Jeff Gold and Vishnu have some very similar plots of things that they tried to get ChatGPT to do with simulated medical note analysis, where they see a very similar pattern that varying things changes. It always makes me think of the XKCD about stirring around the giant pile of linear algebra so the results look right. But I have some general tips for writing prompts, but I also see that I'm kind of running short on time, so I might skip a little bit if that's okay. Through this, I'll be happy to share this information. Okay, so back to the naming test. When I tried to actually use the LLM to do the naming test, our questions start off where, the first rule of prompting is you always want to have a clear metric, right? You want to know what you're doing. Otherwise, you're just trying a million things and you have no notion that it works, right? So we needed to know what we were trying to do. We wanted to know, question one, what levels of accuracy, and then question two, consistency would we get from an LLM at the PNT, right? How accurate would it be and how reliable would those answers be? Because it's useless if it's unreliable. And then across those tests, so the property is consistent across items, right? So are there some items that it is able to do really accurately and some that it can't consistently? And then how does this compare with humans? That one I don't have results for yet. But our setup was we took our 2023 paper where we used BERT for this purpose, and we used the same set of administrations. So it was about 6,500 target production pairs. By dumb luck, it happened to be pretty evenly balanced, which never happens. So we were really glad about that, between ones that were related and ones that were unrelated, according to the ground truth. We tried two LLMs. We tried one openish LLM that I can run here on our OHSU infrastructure for free, or not for free. I pay through the nose for access to xCloud, but not paying per call uses to OpenAI. And that one is a very well-performing but small LLM called Mithril Instruct. And then we also did try OpenAI. We tried ChatGPT 3.5, not 4 because of the cost. 4 is about 20 times as expensive. And so if you imagine running 6,000 things through it, that 20 times means it goes from about $4 or $5 per experiment to $80 per experiment or $100 per experiment times 5 replicates. And since I'm doing this on my credit card because my grant is almost gone, I thought I can spot the grant $50. I don't want to spot the grant, hundreds of dollars. The way we set up the task was as a binary classification of semantic similarity according to the PMT rules. And the measure that we used, we looked at accuracy, then sensitivity and specificity, because that's what we looked at before. And then we also looked at agreement across replicated runs. We ran the same experiment 5 times through ChatGPT or through GPT 3.5 using their chat interface, not the consumer-facing one, but the developer-facing one, which is important for a reason I'll talk about in a second. And then we do Krippendorf's alpha. So we sort of pretend that we had 5 raters, right? And got a sense of inter-rater agreement. So data and security privacy considerations with LLMs. This is important for any LLM project. You've got sort of your first choice is always, do you use an on-prem or locally hosted LLM, or do you use something in the cloud? A local LLM, everything stays on our computers and never leaves. So that right there solves a lot of data privacy and security problems, right? Cloud hosted, the provider sees the data at inference time, and they see it and maybe keep it, maybe use it, who knows? So this raises 2 types of concerns. A type 1 concern, sensitive data is being disclosed to a third party and then possibly retained by that third party and reused for God only knows what, or stored in an insecure manner or whatever, right? This is not an LLM problem. This is a cloud problem, right? This is a thing that happens with any cloud hosted anything, but it's especially acute with LLMs. And this is managed using the usual mechanisms of BAA, right? Or you might also need to worry. In our case, we had to worry about our data was not PHI at all. It's never been considered sensitive. But we did have to check to make sure our data use agreement, or people that gave it to us, allowed it to be disclosed to a third party. And it did. which was great. But we had to be very careful about this. And in any other experiment, we would have probably gone back to the IRB and asked for, more determinations. In this case, because the data was literally a single word, and we have many times been around this with various IRBs at many institutions, and it's always been considered not anything sensitive, and the data is actually on a public website already, and is widely used in the field. We were like, okay, we're okay for this experiment with this specific data using OpenAI. I would encourage anybody thinking about doing this with their data to be very, very cautious and go through the new AI Governance Committee's approval process as well, and consult them for help. Type 2 concerns, sensitive data being incorporated into future versions of the provider's models. If we just take stuff and paste it into ChatGPT's web interface, they retain those queries and use them to train the next version of ChatGPT. This could be a problem in that this is an exciting new frontier of HIPAA violation, right? And also it leads to data contamination, right? Because now, like, my data that I'm using in my published experiment, my test data, could be part of the training data of the next version of the LLM, and now, like, it might have memorized my data, and nobody really knows, like, how much of a risk that is, but it's totally a risk. This can maybe be managed by paying really close attention to terms of use. On OpenAI, their developer API specifically says that they don't use queries for model improvement in the future. They retain it for legal purposes for 30 days, then it's gone, and they don't use it for retraining. And they say, we do use the web interface for retraining. So that's another dimension of concern. So this experiment, not even remotely sensitive, never been considered PHI, widely used, blah, blah, blah. So we decided it was okay to use with the developer API. But we went through, like, a fairly considered process to make that determination. Then we'd already had a lot of experience using this data set with, machine learning models in a variety of ways. Okay, so the setup. We set it up as a zero-shot classification problem with chain of thought across multiple queries. And I am almost out of time, so we'll just show really quickly, right? We sort of gave it the same instructions that a human doing the task is given, where we had examples of the 6 kinds of relationships with an example for each one. So this is like actually 0.5 shot. It's not zero shot, but it's not exactly few shot, because it's not exactly zero shot though. And then we gave it a very clear instruction with the chain of thought piece, the think step by step, right? Where the model's job is to then reason through what it would answer, right? How it would apply those rules. We did this before we ask it to actually tell us if it's related or not. And the reason for that is, go back to what we talked about context. At the point where we ask it whether it's related, I want it to have as much useful context in that history as possible, including its own reasoning of why it is or isn't related, right? And I want that to be as close as possible to the point where we actually ask it to make that question. When we tried this without chain of thought, and then we tried it, hey, is it related? Yes. Why or why not? It would give just like random ridiculous answers. Flipping it around made a big difference. And the reason is because at the time it made the determination, it knew what it needed to know. And then we gave it the real question, and then asked it to follow up what 6 types are there. So we had like a little dialogue with the LLM, basically is what we did. And each step of the way we were getting stuff out, including the final answer of what kind of relationship it was. So a lot of ways to interact. The simplest way is bare bones. You give a text in, you give a text out. That means that you're now writing more code to parse your answers, and like now you have 10,000 problems, right? Better get out your regular expressions to parse the output, and that to me that way is like is madness. I like tools like Guidance or LangChain, which let you do like much more constrained decoding. Those are a little more complex. But the one we used for this was a really fun one called LMQL, which I quite like. It has some sharp edges to it because it's a research project, but it lets you write kind of SQL-ish looking queries where you can give a lot of constraints and you can mix in Python code so you can have logic. It's really nice. Okay. Results, terrifying work in progress results, all of the hazard warning signs. This is like literally, part of the experiment's literally still running on Xcloud today. Back to the sharp edges. So our baseline was BERT, and BERT worked really, really well at this. And it worked really, really well at this because we fine-tuned the model on this task specifically. So we had very good performance. The open source model had not good performance. It had very high specificity. It was very good at telling when something wasn't related, was not good at sensitivity. GPT 3.5 was more than marginally better, but still not as good as BERT. And we We think if we were using GPT-4, it would probably be a lot better. Just anecdotally from noodling around with it, it really does do a lot better, but we don't have funds to try it right now. So when we have the money, we'll try it and do it for real. We also applied for a research grant from OpenAI, but they won't give it to us. It's not exactly a fair baseline because they really are apples and oranges methods, but sort of, good to know where we're coming in with a method that we know works. But remember, BERT doesn't have any of the flexibility that the other ones, gave us.
For a lot of the clinical tasks, GPT-4 does a lot better.
I know. It really, really does seem to do better. And I think it would do better at this because the places this one struggles are in associated and category coordinate relationships, which need more kind of big picture context, and GPT-4 really does that better. I really want to try it. The grant's empty, but so that's where we got. But then we started looking at consistency. And we first looked at consistency across 5 replicated runs. We saw pretty consistent performance, right, in these numbers. Good stuff. Agreement, however, not so great. So Krippendorf's alpha of 0.76, which isn't awful, but is definitely not at the threshold that people usually look for alpha. And but well above agreement according to the percent expected agreement. And terrible agreement when we get down to the fine grained classification of what relationship is in play. And when we looked a little more closely, we saw that when we look at the ones that are not related, this is across the 5 runs, how well do the 5 runs agree? On the left bar, we see that there were a lot of the time, all of the runs agreed completely that it was not related and they were right? And then here's a handful of runs where the consensus was that it was not related across 5 runs, but there was some disagreement. And here was ones where there was a lot of disagreement and it just happened to get it right. When we look at the ones where the ground truth is correct, we see that it was not nearly as consistent, right? There was a lot more variability. So that's a place that it needs to improve. I'm out of time, so I won't walk you guys through my error analysis. I have some fun output if anyone wants to stick around and see, but I don't want to keep people longer than I'm supposed to. So the short version is there's a lot more iteration that needs to happen, and it is not a magic box. Let's put it that way. So
thank you.
Yeah, with that, I'll end.
Stick around for a
Yes.
minute. If you haven't signed in, please sign in. Sheet and the right there. We use the sign-in sheet to determine how much pizza orders.